Good morning, everyone. And I'm very glad to introduce Benjamin Phrampus as our seminar speaker today. Ben is a research physicist at the US Naval Research Lab. He obtained a bachelor's degree in geophysics from Baylor University in 2011. After that, he continued his education to get a PhD degree in from Southern Methodist University in Dallas in 2015. And then there he studied heat and fluid flow, gas hydrates, and hydrate stability zone from the US East Coast to the Beaufort Sea. And after graduation, he obtained the NETL Methane Hydrate Fellowship to continue his research of gas hydrates on the Cascadian margin at Oregon State University. So he joined the US Naval Research Lab in 2018, and first with the postdoc position, and where he utilized machine learning to inform global process and properties of naval's interest. And he has continued his work there to help maintain the naval's advantage in maintaining security and deterrence. And with that, let's welcome Ben to start his talk.
Thank you. You can hear me online, or you can hear me in here. Okay, everything good? Okay, great. So yes, thank you for the very kind introduction, and thank you for coming. As Kehua said, I am a geophysicist, and I work for the Navy. So as a geophysicist, the first question I basically had was, why does the Navy even care about geology? Why do they even want to hire me? So I thought I would give you that perspective in the room, because it's fairly interesting, and it's why I have continued to work there. Related to that, I'm going to talk to you also about geospatial machine learning, which is a lot of what me and my group does at the Naval Research Laboratory. And at the very end, I'm going to introduce an application to Arctic gas hydrates. But in the end, basically what I'm hoping is that you can get an idea of how these types of ships, those that collect wells and core logs, and this is a little weird, these ships over here, that collect like UNOLS vessels that collect sub-bottom profiler data and multi-channel seismic, how we can use that data to help inform these ships, right? The operational Navy, those ships that are actually out in the water right now. Just for a brief outline, I'm going to first introduce you to the fact of why the Navy cares about geology. It turns out there's four main reasons. The first of which is acoustic propagation. This is related to ASW or anti-submarine warfare. The second topic is mine warfare. Typically, this is related to UXOs, which stands for unexploded ordnances. We also care about seabed infrastructure, such as submarine cables. And recently, this idea of alt-nav, or alternative to GPS navigation, has become a big topic. And I'll introduce that to you as well. Related to that, I will then talk about geospatial machine learning, kind of in a very broad sense, and then show you a specific application. I did just want to bring up that actually this week, this past Sunday, 60 Minutes had two of their three parts were actually on the US Navy and their response to the China naval buildup. I'm a scientist. I will be giving you a scientific perspective, but obviously there is many more perspectives for what the Navy does and what it needs to do. And if you're interested in some of those topics, I would suggest you give this a watch. It is interesting. I figured I would start this by actually talking about the Navy and NRL's missions, and that's because this is actually very important. So the Navy mission statement is to recruit, train, equip, and organize to deliver combat-ready naval forces to win conflicts and wars while maintaining security and deterrence through sustained forward presence. I've highlighted a few different phrases up there, and what I take away whenever I read that, just as a research scientist, is that the Navy has to be always ready, that is ready right now, and it basically has to be ready at all locations, because it has this idea of maintaining and also forward presence, like always being ready at every location. NRL's mission statement's a little longer. I'm not going to bore you with the whole thing, but I highlighted a section down there that says scientific research and advanced technological development directed towards maritime applications. That basically means we're interested in the marine sciences, whatever that means, in support of the Navy, and we have to be always ready and at all locations. This wouldn't be a talk about the Navy if I didn't bring up The Art of War by Sun Tzu. So I'm going to paraphrase from the 5th century BC, but the art of war is stated by Sun Tzu to be governed by 5 factors. That is the moral law, heaven, earth, the commander, and method and discipline. Heaven is described as night and day, cold and heat, times and seasons. This basically means meteorology. Earth is described as distances great and small, danger and security, open ground and narrow passes. This becomes your oceanography and your geology. So what this shows is that for the art of war, if you're a good earth scientist, you're 2/5 of the way there, right? So the earth sciences matter. Sun Tzu says these 5 heads should be familiar to every general. He who knows them will be victorious. He who knows them not will fail. And this is important because sometimes we forget. This is just an example of a headline from approximately 2 years ago where a submarine ran into it was called an underwater object here. It turned out to be a seamount, right? A submarine mountain that the Navy didn't know was there. And the submarine ran into it, right? So he who knows them not will fail. So specifically geology, why does the Navy care? The first reason they care about is acoustic propagation. So as an example of this, we can have a receiver, maybe it's a ship at the surface, maybe it's a submarine at depth, and there's also some sound source. And as many people here will be aware, because many of you are geophysicists, the sound propagation depends on your sound speed profile, right? So if you have a negative sound speed profile, your energy will be refracted downward. If you have a positive sound speed gradient, then your energy will be propagated upward. And if you have an isovelocity, your energy will radiate out in all directions equally. So if we take these ideas and we apply this to the water column, right, we can have a positive gradient and a negative gradient. And what that will mean is that if I have a sound source up in this upper section of the water column, that we can propagate energy that gets kind of focused near the surface. This is called a surface duct. And we can also have energy that gets below that transition depth where it gets reflected, or excuse me, it gets refracted downwards. What this results in is a shadow zone. So what that means is if I have a submarine down here trying to track or trace this submarine up here, I'm not going to be able to detect them because I'm in that shadow zone. I'm never going to hear them. Of course, we can add complexity here. So here's just a little bit more complex sound speed profile where we have that surface duct again, but we also have a sound channel. But in this cartoon, I've also added in the bottom, right? Because this bottom, the geology actually ends up being important. And that's because this energy could actually come down, interact with the bottom, and perhaps reflect upwards. So if we go back, right, if I have energy that propagates downwards and reflects off the bottom, it can insonify that shadow zone. Now, all of a sudden, if I'm in that shadow zone as is marked there, I can actually detect that other submarine. So my understanding of the environment and being able to understand if and or when I will have that type of energy returning becomes very important. So the Navy needs to know acoustic propagation within the ocean, and how does that interact with the seabed? Well, one of the ways is just directly due to the bathymetry. Here we have an example of some propagation models. The warm colors basically mean that's more acoustic energy. The blue colors mean there's less. So we can see in this example, we have a flat seabed, we have some source, and we have a lot of propagation in the water column. But in this example over here, if I put in a seamount, all of a sudden I strip out a bunch of that energy. So if I'm on the opposite side of that seamount, all of a sudden I have very low signal detection. I may not be able to detect whatever's making that source. Another idea down here is actually enhancement. You have upslope and downslope enhancement. Basically, this is just how the bathymetry looks, and that it's possible that depending on where you are and where your bathymetry is, that you can actually enhance the signals in the water column. So your bathymetry becomes important. There's also this idea of attenuation, which is that whenever the energy interacts with the bottom, does it propagate? Does it attenuate? What happens to it? Just as an example of this, here we have a model for a low attenuative environment. So we have a lot of propagation, right? We maintain a high level of energy in this sediment. Here is a high attenuation example, right? All of a sudden I have no propagation at all, right? The energy will not propagate through this medium. And then of course we can combine this where we have low propagation and then we enter into a high attenuation zone where we have no propagation, right? So understanding this attenuation and how this acoustic energy can be lost becomes very important. So what this means is that we need to understand something about our bathymetry and about the attenuation, but we need to understand this at a wide range of frequencies, from 1 hertz to 1 megahertz. We need to understand this at many different angles because how we insonify the bottom depends on that angle, and all angles end up mattering. And we need to understand this for basically all geology, chemistry, biology. So what this means is that we need to know our geoacoustic properties. We're also interested in things like mine warfare and unexploded ordnances. Here is just an example of, this is from a field test, so these are like synthetic warheads, but it turns out these things exist in reality, right? So this is a photo from the British Royal Navy from a few years ago where this tanker dropped an anchor, and when it pulled up a torpedo with it. That is scary. We do not want that to happen. Everything was fine with this. I actually think this was like already inert. They didn't have like disarm it or anything. So there was actually no danger, but we still don't want this to happen. So what we care about is how these types of ordnance and these types of things on the seabed, how they react to things like water bottom velocity. Come on, you can get over there. Like water bottom velocity. So this is just a very simplified example where we have an initial penetration depth, that is whenever this ordnance would hit the bottom, how deep does it go, versus water velocity. And we can see in this example that there's possibility that these ordnances will always remain buried. That is, that they will enter the seabed and they will not come back out. But they can also be exposed or transitly exposed, or maybe they're exposed and then buried, exposed and then buried. Or there's also a possibility that they're mobile, that you put them on the seabed and then they're going to migrate and move around. So once again, understanding this becomes very, very important. So we need to know something about sediment transportation, sediment erosion. We also care about seabed infrastructure. As a quick aside, I was trying to compile this slide, and I learned that the first transatlantic submarine cable was laid in 1858. I mean, it just blew my mind, so I wanted to share the fact. But it turns out the seabed infrastructure is really important, of course. So actually, it led to the discovery of submarine turbidity currents. That was back in 1929. A 7.2 magnitude earthquake off the Grand Banks of Newfoundland broke six submarine cables over 13 hours and about 500 kilometers. It was estimated that it was in between 100 and 150 cubic kilometers of sand and mud was moved, and it moved in between 60 and 100 kilometers per hour, right? So the seabed infrastructure actually directly led to this discovery of these submarine turbidity currents, which can directly affect seabed infrastructure. Of course, nowadays we have a lot more seabed infrastructure. This is a map of all the submarine cables in the world, and I'm sure everybody here is aware these are extremely important for things like communications. So maintaining the security of these, whether that be from a natural threat like those turbidity currents or not, is also very important. So once again, we need to know something about seafloor stability. This final topic to bring up is alternative to GPS navigation. This is becoming increasingly important because the operational Navy is running into GPS signal denial. And it's becoming fairly common. So being able to navigate, whether it's a ship or a submarine or a plane, in the absence of GPS is becoming more and more important. So there's a lot of work on this. There's work related to things like elevation and terrain mapping, but also trying to use the passive fields. And in particular, magnetics is of interest, and that's because magnetics has a high signal strength and a very high frequency content. And that becomes very useful whenever you're trying to navigate, because that high frequency content directly relates to the fidelity of your navigation. So once again, we need to know something about passive fields. Right, so why geology? Well, because all these properties we discussed, bathymetry, these acoustic properties, sediment erosion and mobility, slope failure, passive fields, these are controlled by the geology. The geology matters. Things like sound speed, density, and attenuation, the lithology, shear strengths, pore pressures, biology, chemistry, right? The passive fields, magnetics, and gravity, these all matter. So what this means is we need to know the geology everywhere, right? So how do you quantify geology everywhere? It's a very good question and a very hard one, and that's why I'm here. So anyways, it turns out that the Navy has many different models to address this in other Earth sciences. As an example, the Navy has NavGen. This is a meteorological model. So it produces things like surface air temperature globally. Navy also has INCOM and HICOM. So these are oceanographic models, and it can produce things like sea surface temperatures, but also, of course, properties versus depth. But what about geology? Does the Navy have something for geology to quantify geology everywhere? Something like the bulk modulus? The answer is no, it does not. But we at the Naval Research Lab are working on something where we use geospatial machine learning to try to quantify these properties that are of naval interest. The idea here is that we want to predict properties where no observations exist. For example, in a denied area, an area where we cannot go out and collect new data. We also want to quantify uncertainties, and that is that if we predict a quantity, how certain are we in that prediction? And we can also look at surrogate areas for future data collection. This is the idea that if you cannot go to a location to collect new data, a location you care about, maybe there's another place on the planet that we can go and look at that is very similar and will help inform that location. So basically what we want to do is something like this, where we can go from these sparse observations, right? Maybe you have 500 observations globally, right? And you want to go to something like this, right? Full coverage, where we have this property of interest. This is seabed density, just as an example, where we have these properties globally and anywhere where the Navy would want to operate. So just as a very quick, I know machine learning is like this huge topic that people are always talking about, but just as a very quick overview, what is machine learning? Computer scientists may tell you it's something like this, right? This machine learning is that blue circle in there, right? It's a combination of data science and computer science and artificial intelligence. And it's like, okay, whatever. At the most basic level, machine learning is how to get a computer system to perform a task with no specific instructions. So as an example, if I want a robot arm to pick up a ball, I can program it explicitly, right? You move this direction, you go out this far, you open the hand, you close the hand, you pick up the ball. Or I can develop a system that uses patterns and inference to pick up the ball. To fill in map values, as an example that we just gave, I can explicitly program, well, you take the density and you divide it by this value and you raise it to this power and it gives me this property. Or I can develop a system that uses patterns and inference to predict that quantity. So just as an example of this, if we have a map and these circles here are observations, what I can do is I can build up this, all of these other properties that I do understand about the Earth. These can be things like distance to shoreline, or maybe you can use satellite-derived quantities like the gravity field, or anything that you understand everywhere where you want to draw a prediction. So everywhere where I have an observation, I have a value associated with those features. So then if I go to a location where I don't have an observation, but I still have those features, I can use those features to try to inform what the value should be there. So the idea is, how does each quantity where I have an observation correlate with each quantity where I don't have an observation? And I use highly correlated properties where I have an observation to apply those observations to calculate at each of those locations, right? Or another way to look at it is we have this big pile of linear algebra and we dump data in one side and we keep stirring it until it looks good, right? It's sad, but that is kind of machine learning. So I wanted to briefly go through some applications of geospatial machine learning in the past, some things that we published and some things that we are currently working on. Just as an example of how we applied this, this is sediment accumulation rate. So we have a distribution of data that looks something like this, and we produce a full coverage map of contemporary sedimentation rate. This is sedimentation rate for the last basically 50 years is probably what it's indicative of. I'm going to be showing some of these plots that look like this. These are validation plots. These are observed values versus predicted values. So the idea here is you want to lie along that 1-to-1 line, right? If everything was perfectly on that 1-to-1, you would get an R squared of 1.0. So this is showing that you have a pretty good R squared, right? 0.88 or 0.89, you want to round up. And that's our validation plot, right? This just shows that we have relatively high confidence in our prediction. We've predicted things like in situ heat flux. This is something that we're trying, that's in review right now. So once again, going from a database that looks something like this to full coverage globally. So here's your validation plot. Once again, a lower R squared value, but as you can see, these higher observed values become very challenging to predict. But you do fairly well at those lower quantities. We don't just apply this necessarily to the ocean. I mean, of course, that's where the Navy cares about, but this is also applicable to things like on land. So this is something that my boss, Warren Wood, recently published where they looked at groundwater solute composition on land. So they took databases that looked like this to produce these global maps. But we also have some work that's currently ongoing. This is something that I've been working on, which is predicting bathymetry. Some of you may not be aware, but satellite-derived altimetry is used to predict bathymetry, but it does it at relatively coarse resolutions. And the question is, can we push that? Can we predict at higher resolution? Can we produce more realistic values? Just as an example of that, this is a prediction of the Pacific Northwest. This is at 15 arc-second resolution, approximately 500-meter resolution. So one of the things, so this is just a zoom in of this area right up here. So this is in a comparison to SRTM. This is 2.1. I think 2.3 might be out now. I did this a while back, but we're comparing what they predict versus what we are able to predict. And there's a lot of things to be said about either one of these, but one of which is that we're at least producing consistent resolution in our predictions, whereas SRTM is not. Here's just once again another zoom in to the zoom in, just to try to show some of that fidelity. And then here's some uncertainties, right? So as we talked about before, the idea is we want uncertainties to be associated with this. So these very low uncertainties, that's where we actually have observations. And then we have locations where we think we are more certain and more uncertain in our prediction. We also have predictions of magnetic anomalies, as we talked about before. AltNav is very important. So this is the idea of, can we use these types of survey lines that are shown here to create a full coverage map? And that's something that we currently have some funding to do and are interested in pursuing. We also have work on exploiting geophysical data holdings. So this is the idea that we have a lot of this multi-channel seismic data, like this MCS data. In purple, we have single channel seismic data. We have OBS data, which is shown in the gray. And the idea is all this data exists and publicly available, and it's sitting there. And it's how can we best leverage all of this information to produce more realistic Earth models, but not just Earth models where that data exists, but globally, right? Can I exploit all of this data to help me predict, something out here where, there is no data? Of course, we have funding ongoing for this as well. So with those ideas in mind, I want to show you a specific application that we have used for machine learning, and that's that's being applied to Arctic gas hydrates. So to start with, what is gas hydrate? Many of you here probably already know this, but for those of you who don't, I'm going to quickly go through this. This is the idea. It's not the idea. This is what it is. This is a phase diagram of gas hydrate. So this is depth, which is basically pressure, versus temperature. And this gray line here shows the stability curve. So if you're inside there, gas hydrate is stable. And if you're outside that, methane gas and water is stable. So gas hydrate is this ice-like solid that forms from methane gas and water under these specific pressure and temperature conditions. So as an example here, if you enter the seafloor, which happens at about 1.2 kilometers, you can form this ice-like solid called gas hydrate. It's technically possible to have gas hydrate in the water column, but typically you don't form gas hydrate there because the saturation of methane is so low. And of course, outside of this stability regime, your gas is stable, right? So that's where you get, that's where you get your bubble plumes. So we can take this idea and we can apply this to a continental margin, and it looks something like this, where you have these deep water gas hydrate reservoirs, and specifically in the Arctic, where you're cold enough, you can get permafrost and submerged, and then gas hydrate that lies below that permafrost. So in the contemporary Arctic, you kind of have these types of conditions where you have onshore permafrost and gas hydrate, you have shallow water permafrost, shallow water gas hydrate, and you also have deep water hydrate. So why does the Navy care about gas and gas hydrate? Well, it goes back to those geoacoustic properties once again. So here we have a plot of gas hydrate concentration versus the water, or excuse me, versus the velocity in the sediment. And as you go to higher and higher concentrations, your VP, your compressional wave velocity, shown up here, increases, right? So understanding the concentration of methane within your sediments is important to understanding the acoustic propagation velocity. It turns out free gas is even more important. So here we have free gas. Here we're actually looking at models because I couldn't find good data for this. So if you have a good plot like this, but with data, please give it to me because I had to rely on models for this. But so once again, this is free gas concentration versus velocity. And we can see that over very small concentrations, I put this line at 5%, you have this huge reduction in your compressional wave velocity, right? So these very small concentrations of gas become very important for your acoustic properties. So once again, the Navy and we care about gas hydrate and the presence of gas. Why do we care about the Arctic? Where there's the political reasons, but we care about it scientifically because over the last 20,000 years, the Arctic has undergone probably the largest change globally. Specifically, that's because of the change in sea level, which isn't specific to the Arctic, but the change in glaciation is. So this is a map of the change in ice thickness from 20,000 years ago to today. And you can see that there are regions where you have upwards of 3 kilometers of ice thickness that has been removed. So that has huge implications on your pressure and your temperature regime. Once again, going back, gas hydrates, which we are interested in, are pressure and temperature sensitive. So for the contemporary Arctic, we had these types of conditions, but whenever we look back at the last glacial maximum 20,000 years ago, we actually have this extra condition that we need to take into account, right? This ice sheet that has potentially a cold base, cold being relative, of course, and gas hydrate that can exist below. So our idea here is that we want to understand the contemporary distribution of gas and gas hydrate, right? Because that is what we care about today. So how can we do that? Well, the first way of doing that would be to go out and fully characterize this region, right? Fully sample this, which is impractical, right? We cannot go out and get full data coverage over the Arctic. So the next best idea is that if we can understand the past distribution of these quantities, and we can compare that to an estimate of the contemporary conditions, where these two differ are locations where things are going to be changing, right? So our idea here is that we're going to quantify the last glacial maximum distribution of gas and gas hydrate. We're going to then compare that to a contemporary distribution using basically the same model. And then where those two differ will denote regions of flux. Those are going to be the locations where we anticipate gas and gas hydrate to be changing over the last 20,000 years. So this is our methodology. I do not want to get caught up in too much of the details. I will gladly talk to you about it after the talk, but most people here would be bored about this. But basically the whole idea is that we have a bunch of inputs that go through models to give us a bunch of outputs. And these inputs are all going to be machine learned where we don't have them as full data coverage. So as an idea of this, right, we can get isochore thicknesses, sediment thicknesses, seafloor porosities, things like this, and we can run that through a compaction model to get properties such as porosity versus depth, fraction play, these types of things. We can then use estimates of total organic carbon and ages and pressures, send it through an organic carbon degradation model to produce a distribution of methane in the water in the sediment column. We can then use that distribution through a gas hydrate phase estimate model to get where hydrate exists, and then look at all the phases of the methane. Right? Is it in solution? Is it gaseous methane? Is it sequestered as gas hydrate? There are a bunch of assumptions that go into this, and as many of you have heard, all models are wrong, but some are useful. I'm not going to go through all of these, but I've highlighted a few that I think are particularly important. We're assuming steady state in these models. That is that we run this model for last glacial maximum, steady state. We then run this model under contemporary conditions, steady state. We're assuming that organic carbon deposition is constant through time. This is wrong. We know this for sure, but we don't have estimates for organic carbon deposition through time. So we kind of make a naive assumption that it's just constant. We also make an assumption that 28.6% of that TOC is labile. Labile, excuse me. Labile means that is the carbon that is going to actually be eaten by the microbes and actually produce methane, and that the remaining approximately 72% there does not get eaten and will remain in the sediment. We also assume that there's no advection, basically that everything is produced in situ and it remains there. Of course, this is also incorrect. And of course, as we are moving forward with this framework, the idea is to address a few of these, in particular, this idea of no advection, to actually incorporate time-dependent advection into these models. So these are some of the inputs for the last glacial maximum. These are in particular the most important ones. I'm not going to show them all to you just because it turns out there's a lot of them. But the most important ones turn out to be elevation, temperature, and salinity. Our elevation for the last glacial maximum, what we do to produce that is we lower the contemporary elevation by 120 meters. That's because 20,000 years ago, sea level was approximately 120 meters shallower. Or yeah, shallower, sorry. And we also account for isostatic rebound due to the presence of that ice. So we can see up here, this is what that grid would look like. You can see that there are parts of margins that are now subaerially exposed. And then this is the difference from the last glacial maximum to today. So you can see that there are locations where you have upwards of like 400 meters of elevation change. To account for the seafloor temperatures, turns out we have three different regimes. The first of which is a marine regime, right, where we're still submarine. And what we do to produce those values is we just take our contemporary sea temperatures and we just subtract 120 meters from that and basically just shift everything. But we're also subglacial, right, where those glaciers exist, where those glaciers existed during last glacial maximum. To get these estimates, we use a combination of two different boundary conditions. The first is a pressure melting point under the thickest 66% of the glacier. This is basically a warm boundary condition, warm being relative here, of course. At the thinnest 33%, we assume that there's ablation occurring. And basically this gives us a cooler boundary condition. This is the idea that at the edges, you're kind of sloughing off ice and you're melting the ice at the edges, and that produces a cooler boundary condition. It's cooler because your surface air temperature is extremely cold during the last glacial maximum. So for that property, we used PMIPS-3, which is a simulation from the last glacial maximum. And that produces temperatures that can be upwards of -40 degrees C in the Arctic. For our salinity, we use something very similar to what we did for the temperature, but it is simplified. And that is that we use the same contemporary sea salinity, minus 120 meters once again. And then where we're subglacial, we just put 0 PSU, basically your fresh water underneath the glacier. So the idea is that we can use these types of boundary conditions for the last glacial maximum, plus an estimate of total labile organic carbon, which we can see here, which is machine learned. And we can produce things like this, which is the total mass of biogenic gas produced at the last glacial maximum. So just to highlight a few things here, the first of which is that these plots look very similar, which is not surprising because you cannot produce biogenic gas without the presence of the carbon, right? So the TOC will directly correlate with the biogenic gas that is produced. So there are regions where we see lots of biogenic gas production. For example, in Barents and off the North Slope of Alaska and in the Mackenzie. We can also look at things like gas hydrate. So this is the total mass of gas hydrate that would be sequestered at the last glacial maximum. You can see here that the largest quantities of where we sequester gas hydrate is actually where you were subaerially exposed. Once again, that's because those temperatures were so cold. That cold temperature means your stability regime is very, very thick. So you're able to encompass a lot of gas into that gas hydrate stability regime. We can also look at the production of thermogenic gas. So this would be that residual carbon like we talked about earlier, where we assumed, was it 28.6% was labile. The remainder of that, we can actually convert into thermogenic gas just to try to get an estimate for the amount of thermogenics that are produced. So what we can see here is that once again, these two plots correlate very well because once again, you need the carbon to produce that gas. But there are also regions where you can't produce thermogenic gas, and that's because you just never reach the correct pressure and temperature conditions. And then, of course, we can compare these types of plots from the last glacial maximum to the contemporary. So this is actually the change in the gas phase from the last glacial maximum to the contemporary. Red colors mean that there is less during the last glacial maximum than what we estimate for today. So we can see here that we have a lot less gas than we anticipate to exist today. And that's because once again, those temperatures were so cold in these subaerially exposed regions that your reaction rates become very, very low. So you actually produce very little carbon relative to what is possible to be produced today. We can also look at the changes in the gas hydrate phase. So this is the opposite of what we see on the other side, where we have a lot less gas. Here we have a lot more gas hydrate. And once again, it's concentrated in those subaerially exposed regions. where your temperatures were extremely cold and you had these very thick hydrate stability regimes. We can also look at changes in permafrost thickness, if people are interested in that. I don't know permafrost people in the audience, but once again, the largest changes are concentrated where you were subaerially exposed. And then finally, we can create a plot that looks like this. This is kind of a summary of everything. So in blue here, this shows regions where we anticipate hydrates to be stable from the last glacial maximum to today. So you can see things like the deep water doesn't seem to have changed very much. In red or pink is locations where we anticipate hydrate dissociation to have occurred or to be occurring. Currently, we cannot differentiate between if it is occurring or if it has occurred. But we can see that these areas like that are subaerially exposed or those that were glaciated are regions where we're likely to see gas hydrate dissociation occurring. There's also technically this region, which we call relic gas hydrate. There are a few locations on the map. It just doesn't show up in this. I'd have to zoom way in for you to see it. We call this relic gas hydrates because the hydrate would only be produced during the last glacial maximum, and the contemporary conditions don't have the correct conditions to produce gas hydrate, but it has the condition to maintain gas hydrate. So basically, if hydrate existed in those locations, they could have only been produced back in the past and wouldn't be something that could contemporarily be produced. There's a few locations like that, but not very many. So with that, I ran a little fast. Sorry about that, but plenty of time for questions, I suppose. So some takeaways and conclusions. So the Navy cares about geology due to a few reasons. The first of which is acoustic propagation, also mine warfare, seafloor infrastructure, and alternative to GPS navigation. Geospatial machine learning can be used to inform regions where observations do not exist, whether that's in data absence areas or areas where we cannot collect data. By combining geospatial machine learning with deterministic models, we can provide insights otherwise unobtainable. Just as an example, that would be the Arctic that we were just looking at, where the only way we can get those types of maps would potentially be through full data coverage. But specifically for the Arctic, we saw that large changes in gas and hydrate distribution since the last glacial maximum, that there was less methane gas sequestered during the last glacial maximum, but that was due to the low temperatures and those lower reaction rates. There was more hydrate sequestered due to low temperatures and thicker stability zone. We see changes that are concentrated in regions of glaciation and subaerial exposure, right? Those are going to be the largest changes in the pressure and temperature conditions. It's not surprising. And the deep water reservoirs remain stable over the last 20,000 years. Before I end, I do have to put in a shameless plug, and that is that NRL is always looking for smart and motivated scientists. We are looking for geologists, geochemists, marine biologists, acusticians. If some of the stuff I talked about today is of interest, please come up and talk to me. We do take PhDs, masters, and bachelors. There's also potential for higher degrees while working at NRL. So that is my email address. It will be on this last slide as well, or I have some cards if you are interested, and I will gladly talk to anybody. So with that, thank you for your time, and I will gladly answer any questions.
Thanks, Ben, for his interesting talk. And do you have any questions for Ben?
Oh, I don't know if I'll be able to answer it.
You rely on primarily available sources of geologic data. One of them's been the Scientific Ocean Drilling Program.
Correct.
Which has been going for 55 years, and NSF's just pulled the plug on it for the end of next year.
I did not know that.
Yeah, so one of the questions, the question I have is, we'll be looking around for partners to convince NSF that eventually that was a mistake, but they've put in the majority of the money for decades and they just don't have it anymore. And so how do we start a dialogue with, for example, the Navy to understand that the geology that the drilling program provides is really crucial to these kinds of things and somehow keep it going?
It's an excellent question. I think
I don't expect you to answer it.
No, I mean, well, I'm actually trying to, because this is very concerning, because drilling data is, I would argue, the best data that we can get our hands on to try to answer these types of questions. So it's a very good question. I would suggest that we get in contact, and then I can talk to my bosses and they can start pushing it up the chain, because I think it does matter. Now, whether or not like ONR, the Office of Naval Research, would fund this. Right. I mean, I think there is a strong argument that could be put forth that the Navy cares. Now, whether or not the Navy would pay is another thing, but there's that argument to be made for sure. Yeah, great.
Yeah, thanks for the talk. I really enjoyed. I have one question that is, more scientific, but also like more kind of like, model style. So how do you quantify uncertainties of the final output, given like that you have uncertainties of each inputs, like many inputs you have more uncertainty in each input, but then also how you kind of propagate this uncertainty until actually the final product? Yeah,
that's a very good and complicated question. So my question to you would be, are you specifically talking about like the models we looked at, or are you talking about the machine learning? Or
yeah,
both?
I'm talking like, regardless, not only the input that you have, probably the input from other type of models, but also the uncertainty that you have also in the machine learning actually propagate from the input to the output.
Yeah. Okay. So I guess I'll just talk you through the whole process. Sorry for those of you who are going to be bored by it. There are uncertain observations to start with, right? And how do we propagate that observational uncertainty through our models and through the machine learning? The answer is I don't know. We've been working on it, and I have not found a satisfactory way of doing that. So as of right now, we do not propagate uncertainty in observations through our system. We can quantify uncertainty in our prediction methodology. We use what is called a conformal prediction. I can give you the citation if you're interested in that type of thing. I think it's very powerful. Basically, what this does is it quantifies the uncertainty within your model using something like a test set, and then uses a metric called non-conformity. Basically, this idea of at a prediction location, how similar am I to other locations where I have observations? The idea here being that if you're similar, your uncertainty is going to be small. And if you're dissimilar, your uncertainty is going to be large. And then we can get these maps of uncertainties. So from there, we have uncertainties in basically every machine learned property. For the model, we can just run ensemble models where we take like the mean value, our predicted value, run that through the model, but then we perturb each of those inputs, typically randomly, but we can also do it systematically if you want. And you perturb those, and then you run those systems over and over and over again. And then you can get this a quantification of the uncertainty. That is how we do it right now. I do not find that very satisfactory, mostly because these models are complex. And whenever you perturb every single input, your uncertainties become very large very quickly. And I don't really think that is accurate. I think we probably know, I think our uncertainty is probably smaller than what we are currently predicting in these models. Now, the uncertainty associated with the assumptions, totally different thing. But under those assumptions, I think our uncertainty is too large. So hopefully that answers the question.
Yeah, thanks.
Thanks for the talk. This is kind of a follow-up question.
Mm-hmm.
In your uncertainty map you put there from the machine learning, there is a big chunk of high uncertainty. And without knowing the process, I would assume that it's probably because it's a highly fluctuated bathymetry or some topography on a very small scale that largely grows. And so, which is kind of unquantified, you don't have observation on that region. Not this
So
one. The
were
uncertainty.
these specifically what you're referring to?
No. The uncertainty that you showed.
Further back?
Yeah. Further
Oh, you're
back.
talking about like the validation.
Yeah.
Okay, yeah, let me get back to one of them. Too many slides. Oh,
Yeah.
forward.
Sorry.
There you go. No, you're good. Like here.
No, not this one actually. The one
this
that
one.
you had like blue lines, which you have very low uncertainty, across the map.
Oh,
Bathymetry, yeah.
Yes.
Yeah, this one.
Okay.
So,
got it.
okay, if you look at the big chunk over there, the high uncertainty circle, yeah. That's highly correlated, I think, with some elevation that he didn't kind of well quantified. And this is, if you propagate it, I'm thinking in the gas hydrate kind of regime, if you take the pockmark in Niega, pockmark in offshore Norway or the Svalbard, there's hundreds of small scale pockmarks, which is 50 to 200, 500 meter scale, which individually, okay, their fluxes are low maybe, but cumulatively it's high impact. And those will fall in those kind of uncertainty regions. So how can you derive global estimation or that Arctic estimation, if
Yeah.
if those are possibly beneath your detection threshold, I would
Yeah,
say.
that's a fantastic question. And the answer is I don't know, right? Because ultimately, so you guys are really getting into the details of this, and it's funny. I just gave this talk to Sandia National Labs, and I reframed this talk to be like much more detail oriented, and they asked me 0 questions about the details. And I came here and I gave you guys a more general overview, and you're asking me all the detailed questions, since I should have given you the other talk. Anyway, I find it funny. So this is very hard because ultimately within these types of systems, we're basically predicting bulk statistics over finite resolutions, right? Basically what that means is the resolution of this, as an example, was 500 meters. The bathymetry at any 500 by 500 meter resolution pixel is variable, right? It's not going to be constant, of course. So inherent in every pixel, there's going to be the statistic that we were trying to quantify, the mean or the median value of that cell, but there's also some variability associated with that. So my answer to be how could we quantify something like that would be to look at the variability at different locations where hopefully in those locations like you were talking about, where you have those pock marks, which are your sub-pixel scale, the variability associated with those locations would be very high. So you could propagate not only your uncertainty, but also your variability, and then potentially your uncertainty in the variability through your system. To quantify this, though, becomes very challenging because we need high enough data to be able to do that, right? I can't quantify a variability with 1 data point, or I would argue not even 3, right? How much data do I need to quantify variability? Potentially a lot, 10 data points, is that the lowest? Like, I don't know. But ultimately, if we have large enough data sets, with bathymetry, we may have, right? If you have large enough data sets, not only can you quantify bulk statistics like the mean, but also the variability, for example, the standard deviation, and then propagate both of those through your system. As of right now, we are not doing that. We have not worked on quantifying variability, mostly because the vast majority of the things I have shown, of course, in the absence of bathymetry, doesn't have data resolution that we can quantify that. Hopefully that answers the question.
I have a question. Could you go? Oh, sorry. Okay, sorry. Could you go back to the slide with the Last Glacial Maximum and the assumptions that you made? I really enjoyed this part of your talk, and this is a really fun project. Oh, the next one. Oh, these are fun. Yeah.
Okay.
I love the Last Glacial Maximum, so I'm really biased here, and I think like in terms of both temperature and salinity, I find these assumptions about what the ocean would have looked like kind of unsatisfying, but I don't know how much it would actually matter. So my first question is like, how sensitive is the final result to uncertainty in both temperature and salinity? If you were off by like 5 degrees or 10% of PSU, would that even make a difference, or are the results pretty robust to that?
So in terms of these plots that I have showed you here, there's no uncertainty in these, right? Because this is just like the mean value. So it would have 0 effect on this. The uncertainties, as I said before, they are large with relatively conservative estimates of our uncertainties. So if we add more uncertainty, I mean, our uncertainty thresholds are just going to get larger and larger. If you find these unsatisfactory, because I do too, I would be really interested in talking to you about what we could do to improve these. So just as an example, we're working with a glaciologist at the University of Tromsø right now. So instead of making these simple subglacial assumptions, he's running thermodynamic models to try to estimate the temperatures at the bases of these conditions. So, you know, if PMIPS isn't the correct thing I should be using, what should I be using? Because I would gladly do it. It's just, this is kind of the best I was able to do as somebody who is not an expert in all of these things. So if you have suggestions, please give them to me because I want them.
Okay, cool. I'll share some specific ones later, but actually I had another question quick that relates to that. And it was going to be like, we do have this paleo data that is it's like sparse, and it comes from sediment cores, and it might tell you something about like paleo temperature, paleo salinity. Have you considered using the same methods that you use for filling these gaps in the modern to try to leverage that data towards coming up with something for the LGM?
Yes. So once again, man, you guys are like nailing it. I have like slides on this in my other talk. Yes and no. How do I want to go about this? trying to predict quantities specific to a given time, we have done before. And how we have gone about that is that those different features, like I showed you before, that we use to try to predict, what we do is we use features that are indicative of that time, right? So crustal age is just a good example, right? If I want to predict a quantity on a global scale and I care about something 50 million years ago, well, what was my crust age 50 million years ago? Well, I take the crust age map, I might subtract 50, and I just use that. And then everything where I'm 0 or less, basically I say it didn't exist then, right? So I can like get rid of it or something like that. You can also use things like plate reconstructions, right? And move things around and use those that are indicative of those times to predict. To date, those predictions don't look very good. One of the problems is the data, you think contemporary data is sparse. Let's go to paleo data. That's even more sparse, right? So our problem becomes harder and harder. Another thing that we are doing is we're actually working on systems that instead of predicting just maps, we're predicting basically volumes, where we're predicting with depth, right? So you can think about this as basically trying to produce a well at every location that you go to. So that would actually be kind of akin to what you're talking about, where you're predicting whatever the quantity of interest is. You're not only producing something for the contemporary, but something for, you know, every 1 million years or whatever, right, with depth. I have a project that's currently doing that. Preliminary results look surprisingly encouraging, but we're very, very simple as of right now. So as we build forward and become more and more complex, I don't know how it's gonna work, but we are working. Yeah.
Hi, Ben. If you can go back to slide 25, I think.
25.
And these are high-level comment about machine learning.
Sure.
Your data, your input data is very sparse.
Whoop.
And I
Yes.
think it's highly skewed towards northern hemispheres.
Yes,
But the prediction, you are making it all over the world.
correct.
So my question is, how confident are you of those predictions where you don't have data? It seems like you're creating information out of nowhere.
I mean, I'm not. I'm using that information to get that. I mean,
So,
no,
yeah.
it is a good question. The whole idea here, right, is that, you know, these locations right down here, there's nothing in the South Pacific, right? So the whole idea here is there locations on the planet that are similar to the South Pacific, right? And I would argue yes, right? And then is there data in those locations? Well, maybe, maybe not. But what we're doing here is we're using the locations globally where we have data that are most similar to these locations to make a prediction. And then, as we talked about before, somebody asked me about uncertainty, how we quantify the uncertainty in that prediction. Sorry, I'm just not showing you uncertainty here. I really should, but I'm not. How we quantify our uncertainty is by a metric of nonconformity. That is, how similar is this location down here to somewhere where it thinks is similar, right? And that is that if it thinks it's very, very similar, then our uncertainty is going to be very low because it is similar. But if it's not similar under this nonconformity metric, then our uncertainty is going to be high. So how accurate or how good do I think this prediction is? To answer that, I would show you the uncertainty, which I don't have on me. I'm sorry. I would show you that uncertainty, and I would say if that uncertainty is low there, I would believe it. I would believe it in so much as I could believe it, right? Because this is a prediction. This is wrong. Like, I know it is not this, right? That exact value, if you go to that cell, right? This is two-minute prediction, right? This is a 4x4 kilometer, 16-kilometer area. So if you go to one of those 16 by 16 kilometer areas and you stick a probe into the ground, is it going to be exactly, 84.1 milliwatts per meter squared? Probably not. If you do a grid over that 4x4 kilometer area and you sample every 1 meter or 1 kilometer and you do a bulk statistic of it, I would bet money that it would be pretty close to, it would be close to, to that value, right? Does that answer your question? Okay. Maybe not satisfactory, but Alexi.
Dan, I love your work, so I'm not gonna give you a hard time on your machine learning. You just asked ChatGPT, I think, what's happening there.
Yes.
Can you go to one of your last slides with your hydrate purple color? The change between the LGM and the modern.
For the hydrate specifically.
Yeah, the one which you said like your major result.
Yeah, it goes. Oh, that plot.
Here.
This one right here. Yeah.
And you said and I understand why you said that all the purple is either has already dissociated or is dissociating right now, and you don't have an answer to that.
Correct.
Which is fine, but what is the best approach to find the answer to that? Is it
Yeah.
trying to numerical model this, trying to get more data to that? Because this is an important question, right?
Yeah, so on this scale, is that what you're asking about? Like specifically on this type of scale, like for the Arctic as a whole? I think if I can go back to my, all the assumptions that are in here, right? The reason I can't answer that is that I assume steady state in both conditions, right? Which means that there's no transients. So the first step would be you need to apply transients and you need to apply advection into these systems. That would be the first step. And those are the two things that we are trying to incorporate. But those are hard things to put into these systems, right? So that is how I would go about trying to constrain that on this type of scale. Of course, you can go to finer scales where things become a little bit easier because you can collect data and actually be data constrained in those regions.
So yeah, we have just a bit of time, right? I guess I have two questions really. One is in the places where we have data that's outside of this. So for instance, if it's a CO2 release in terms of a methane release in terms of the hydrate system, or if it's visible, bottom simulating reflectors for hydrate, have you attempted in, say, that last model to attempt and do sort of a third-party check on the patterns that are seen in the map?
So yes, like at some specific areas, right? We've like what's the base of hydrate stability? What did we predict the base of hydrate stability to be? Is it within our uncertainty? Like that's kind of how we've done it. It's been spot checks, right? Like we pull a few areas, we look at it, and if it's within our, we do everything on like 1 sigma. It's like if it's within our 1 sigma uncertainty, we're like we're doing great because we're predicting on such a big scale. If we can go to a fine scale observation and we were within uncertainty, we're happy. So we have done those types of checks. Have we done it for like all the data or anything like that? No.
Right, but
It'd be great to
individually, yeah. So then the other thing is, I'm actually intrigued by the potential to use the predictions. Say we could use the heat flux one that you were just showing earlier as a way to test what's actually controlling what, because you're making assumptions that something is similar because therefore there's something about the geology that makes it more similar. Maybe it's tectonic setting, maybe it's spreading rate, whatever it is.
Right.
Where it isn't that, there's then geology to learn, right? The controlling influences.
Yeah.
I'm curious if you guys have gone down that.
Yes.
Maybe that's a rabbit hole, but
no,
maybe
it's not. That is something. So I brought up this fact of like surrogate areas, right? So if I care about this region over here, what's the most similar place on the planet to go and collect data to maybe inform that location? Another thing that we can do, and we always do, is we call it parametric isolation. And that is, I have all those features and I have a bunch of observations. Which location globally is the least similar to everywhere else where I have an observation? So that is the most unique location on the planet. Excuse me. That is the most unique location on the planet relative to where I've sampled before. And that's where I'd want to go and collect their data because that's the most unique place. I've never seen anything like that globally within that database. So we have these maps. Once again, I just don't have one for you. I'm sorry, but basically you get these hotspots in locations where it's like super red and then everywhere else is like black, right? Because it's like everywhere else is kind of similar, but this location is so unique relative to everywhere else that maybe I want to go collect a density measurement or a heat flow measurement or a porosity measurement. Yeah. We jokingly always called that like our proposal generation. Like, it's like, yeah, you run a prediction, it says go here, you write a proposal to go collect data, and you run it again, like you just keep doing it.
Okay, I have a last question.
Sure.
So I'm going to predict the transient gas hydrate and permafrost evolution at Arctic continental margins. And, heat flux is a critical input. So how confident is your heat flux prediction in Arctic?
Yeah, I don't know. I'll have to look at the uncertainty. Somebody else basically asked something similar. But another thing, so I want to bring this up. Nobody asked me about it, but I'm going to bring it up. I don't know if there's any heat flow scientists in here, but that heat flow estimate that I showed you that we're trying to get published, I called it in situ heat flux. So what that means is this is what we anticipate if you go to a location and you like stick a probe in the ground and you do a bulk statistic over a finite area, right? So it's very esoteric quantity. The reason I'm bringing this up is that if you want to use these values, this is akin to you going and collecting a heat flow measurement and trying to use that value. There are a bunch of corrections that you need to apply to heat flow measurements, depending on where you are. There's a bunch of corrections you have to do to apply to those heat flow measurements to be indicative of, for example, the conductive heat flow within the system, right? So you can use this as a proxy for going and collecting a data point, but there's still a bunch of corrections that need to be applied if you're only interested in the conductive heat transfer. Because we do not separate out conductive and advective heat transfer within this prediction, whereas the majority of what has been done in the past tries to differentiate these two. So just to bring that up. In terms of how certain am I would look at those uncertainties, and then we can look in the Arctic and see, like, is it bad? Is it good? I don't know, because once again, I just didn't put the uncertainty up here. Sorry.
Thank you.
Yeah.
And thanks Ben again for his interesting talk.
Thank you.